Hello class, Professor Anderson here. Let's talk about angular momentum, and specifically let's talk about the conservation of angular momentum. When we talked about momentum, we said that it is one of the sort of foundational principles, this idea of conservation of momentum, right? In elastic collisions or in inelastic collisions, momentum is conserved. Turns out that angular momentum is also conserved. Namely, if things are spinning, they tend to stay spinning. Okay? So, angular momentum is just this. Angular momentum L is conserved, and we have the exact same caveat that we had with linear momentum if there are no external, not forces in this case, but torques. Angular momentum L is conserved if there are no external torques. All right, so what do we mean by this? What we mean by this is the following. L, which is a vector of course, initial has to equal L final. All right, this is the idea of conservation of momentum. Within each of those L's, you have to account for the entire system. Okay, so you have to look at the system initially, you have to look at the system finally. And if there are no external torques acting on the system, then it's conserved and you should get the same quantity. All right, so let's try a very simple example. Let's say that we take our good old ball on a string. Okay, we love this example because it's easy to do. Here's our ball on the string. It's going around like this in a circle. Okay, and this is a top view. Okay, so we're spinning the ball around in a horizontal circle, and we're looking at it from the top. Let's ask the question, what happens to the speed of the ball if we suddenly shrink the chord to half its original size? And you can imagine doing this the following way. Like if I'm holding up a string and I'm swinging it around, I'm swinging the ball around in a circle, and now I pull the string down through my hand, I can change the length of the string as the ball is still spinning. Okay, so that's sort of the picture that we're going to look at here. So we'll take this example and we're going to say as R goes to R over 2, what happens to V? All right, let's see if we can figure this out. Ball spinning around at some particular V initially. We know that conservation of angular momentum says the following. Li equals Lf. But we also know what the angular momentum is for a ball on a string. It is mvr. And so if it's initial, I need to put subscripts on there. mv initial, r initial. What about the final? Same mass, so we don't have to worry about that. Again, we just have mvr. So when the ball gets to half its original length and it's going around, we had V initial before, now we have some V final. And let's see if that's bigger or smaller. Okay. All right, we want to solve this thing for V final. V final is equal to what? Well, the m's cancel out. That's really nice. And we're just left with R initial divided by R final, all of that times V initial. In our case, we said that R initial was just R. R final was R over 2. The r's drop out, the half on the bottom flips up to be a 2 up on the top, and we get twice the speed. Okay? As that object is pulled in by pulling on the string, it starts going faster and faster and faster. So when you're at halfway in, it's going twice as fast. If you went to a third, it would be going 3 times as fast. And in fact, in the limit, as this thing goes to 0, it would be going infinitely fast. Okay? It would be orbiting like this. This is kind of like what happens when something gets sucked into a black hole, right? It starts spinning faster and faster and faster as it goes around. It's kind of a cool idea. Okay, hopefully that one is clear. If not, definitely come see me in office hours. Cheers.